title of this workshop is Digital Technology Deployment in and to be able to join you at MERcon 2021 in Sri Lanka, all the way from my home office in Manchester. And yeah, so I guess that's one of the positives. So if like online events and virtual conferences, we can easily join you and all get together. I can see some familiar faces of some of our PhD students from Manchester as well, which is great. And it's great that so many of you are interested in our workshop and in digital technologies for apparel product development. So before we get started, I just wanted to cover a few housekeeping rules. So I'm sure most of you will be familiar with Zoom meetings now, but just to minimize background noises. So I know everyone is actually muted at the moment, but we would like to ask you to stay muted. And we have the chat function enabled, so feel free to use the chat to ask any questions throughout the workshop. We'd like to hear your comments as well, and if you've got any experience with digital technologies, feel free to chip in and share your experiences in the chat. If you'd like to join the discussion, please use the raise hand function, so familiarize yourself with that. It's under reactions. So if you don't want to be featured in the video, please feel free to switch your camera off and stay muted. And lastly, if you're a student and you'd like to get a certificate for participation for this workshop, I've been told you're required to stay for the duration of this workshop. So just keep that in mind. So I'd like to... Can everyone see my screen okay at the moment, my slides? If I just get a...
Yes, Christine, we can see.
Yeah, that's great. So just move on to introduce the team. So there's 4 of us today running this workshop together. We've got Dr. Jayamali De Silva and Dr. Ranga Abhay-Surya, who most of you who are in Sri Lanka at the moment from the University of Moratuwa will be familiar with. They are both senior lecturers within the Department of Textile and Apparel Engineering. And then we've also got Dr. Simeon Gill, who is the senior lecturer in fashion technology at the Department of Materials at the University of Manchester, and he's one of my colleagues. I'm a lecturer in fashion technology at the same department. So you may have come across some of Simeon's publications if you've done some research in sizing or automated pattern making or body scanning. And Simeon and I work closely together in the ADE Apparel Design Engineering research group. And so the 4 of us get together because we all have an interest in digital technologies for apparel product development and different aspects of that. And we thought it would be good to bring all of these different aspects together and present them to you today, and also look at some of the opportunities and limitations, and maybe get some ideas from you as well in terms of going forward, what's needed for the future of digital technologies in the apparel and textile industries. So the link between us started between Jayamali and myself, actually, because Dr. Jayamali came to Manchester Metropolitan University as a visiting PhD researcher, and I was doing my PhD at MMU at the same time, so we shared an office, and that's how sort of the collaboration started between us. And hopefully going forward, we'll be doing some more research projects together. So yes, so good, nice to see your video there, Jayamali. So I just go through the workshop outline for today. So we've planned about 2 hours for this workshop. A pre-warning that we might overrun, but we try to stick to the 2 hours. So following the introduction, we've got Simeon talking about his research on apparel sizing and some questions and answers as well. So feel free to put these into the chat so he can address them after the presentation. And after that, we've got Dr. Jomali De Silva talking about 3D CAD modeling for virtual prototyping applications in apparel. So he will have some demonstrations as well and some poll questions for you to get some input from you as well. And then Ranga will talk about digital technology for cutting and packing 2D shapes, and eventually Al will talk about some of the limitations of applying digital technologies within apparel product development. And I'd like to hear from you as well. What do you think some future solutions might be? So this is the aim and the objectives for the workshop. So the overall aim is to demonstrate relevant digital technologies which are used in apparel product development and measure the digital maturity within the Sri Lankan apparel manufacturing industry, because I know we've got quite a lot of students, obviously from the University of Moratuwa, but also some professionals from the manufacturing industry in Sri Lanka here today, which is great. So these 4 objectives here relate closely to the 4 parts that each of us will present. So looking at the sizing and body scan, prototyping, typing to be covered by Jayamali, and then also the computational geometric concepts, algorithms and tools for cutting and packing, which is based on Dr. Ranga's research. And finally, the limitations and the opportunities that I'll be looking at. So as I said, so this is a workshop. We don't just want to talk at you, we want to get your input as well. So we'll be using Turning Point throughout this workshop to run some polls and get some ideas from you. So if you'd like to take a moment I will actually put this in the chat now as well. So you can either access it via your mobile or a browser, and then type in the session ID, which is MERcon 21. So there's no need to create an account, and your responses will be anonymous. So if you'd like to join the session now, then we can maybe start to our first question to just make sure that the poll actually works, and to get to know who's joined us today here in the session. So if you've managed to join the side, so the session ID is MERcon 21, and I've got it on here again, the website. So you should be able to see on your device now this question popping up. So if you just could tell us who you are. Are you an undergraduate or postgraduate taught student, a research student, academic, or professional from the apparel or textile industry, or maybe from a different industry? If you could just pop in your response now, that would be great. If you've got any problems with accessing the poll tool, let me know. Okay, and it's great to see some of your responses in the chat as well. So you've got an academic, research student, as well as professional from the apparel industry. Great, nice to meet you. Another research student. That's great. We're getting a few responses now. So I think you've all managed, some of you have managed to join the session, which is good. I'll turn it in, a Turning Point. Hi Tafa. Tafa said she's a research student. She's actually one of my PhD students and Simeon's PhD students. Great that you could join us. Okay, so I know some of you are putting the responses in the chat. That's fine too. But if you can join the poll that would be great, because we've got quite a few other poll questions throughout the session. And Phil, research student. That's great. We're also glad if you could join the workshop, and welcome. Okay, let's see what some of you answered. Okay, so we've got a mix here of some undergraduate students, some research students, and also some apparel and textile business professionals. That's great. That's really good to see. It's actually quite a balanced participation here. Great to see that even the business professionals have found some time to join us, and we really look forward to your input throughout the workshop. Then I've got one more question here. Which digital technologies do you use for apparel product development in your business or research? Again, if you go to and then answer the question. PhD student, undergraduate, hi everyone. Yeah, keep using the chat. We like to hear from you. Some of you are putting the answers in the chat as well to this question, which is fine. So we've got B's and C's quite a lot, which means 2D CAD for pattern making and 2D CAD for marker making is used quite a lot. But let's see what we've got on the poll. Okay, yeah, so we've got 2D CAD for pattern making and 3D CAD for virtual fit and prototyping. That's great, because we'll be covering that today, and especially Jamali will obviously be covering the 3D CAD for virtual fit and prototyping. So that'll be interesting to hear your thoughts on that as well. Okay, that's great for a start. Good to have a bit of information about you and your backgrounds. And we've got a final question here, which is, what is the greatest benefit of the digital technologies that you apply in your business? Would that be? You can type that into the app or into the poll if you've joined the poll. We have a couple of responses in the chat as well. So it reduces the lead time, customer satisfaction, time saving, avoid sample making time, reduce time consuming, reduce lead time, cost, but yeah, it's lead time and cost. Okay. So it's a lot about time saving, yeah. Okay, so we've got a few more responses here on the poll. Value addition, creating better productivity and efficiency, yes. Great. Okay, I'll wait for a few more responses. Time management and accuracy. Okay, let's see what you come up with in the poll. Okay, so here we've got data integrity as well, improvement for efficiency, easy monitoring, time saving, speed. So a lot of it is related to lead times and speed, reduction of time. Yeah. Yeah, which is great. Okay, so thanks for your input on this. It's good to have a bit of background information. And now I want to hand over to Dr. Simingulu, who will be talking about his research on apparel sizing and 3D body scanning. So over to you, Simi, and I'll stop sharing now.
Hi, thank you, Christina. Right, I'll just get into the process of sharing my slides so you can see. I think with there, I share that, make that full screen and start from the beginning. I think I've got to flip over these display settings. Okay, hopefully now you're seeing the presentation slides. So as Christina had said, I work with her. You can see her on the picture here. This is some of the people I work quite closely with as part of the Apparel Design and Engineering Collective. And it's quite important, really. And you can see in the bottom corner that scanner as well. That's an integral part of some of what we do. Although I am told as we move forward, that'll be replaced with a little mobile phone that will theoretically do a similar thing. So there's quite a range of skills, and I really enjoy sort of research with a broad range of different people and different perspectives. And I think that allows us to do some quite interesting work within apparel design engineering. So, you know, in terms of technology, which we're here to talk about, you know, harnessing technology to better develop body-worn products requires we lead the current practice to a state can be adopted and integrated. So what we see is lots of promise with technology, but then often these quite difficult problems with actually engaging it because, oops, sorry, I think I've moved forward a slide. There we go. And that's quite important to try and find a way for people to engage in it effectively. So in the past 50 years, we've kind of moved from individual production skills, mass manufacture, centralized skills in making body-worn products. And what that means is that lots of what used to be home-based skills and skills that were distributed through a population are now largely concentrated in the hands of a limited number of people making stuff. And I think that then brings with it certain problems, not least of all with access to technology. But technology does offer us a lot, ways to center the body in product development, access not afforded to those who would most benefit. So, you know, I think that's quite important, which is that we have this technology, but it's often very expensive and quite difficult. And it's something we've done with apparel design engineering is try and reach out to people and allow them opportunities to access technology in a way that means they can have some connection with it. So as educators, bridge the gap, but it requires more accessible means to engage the wider maker community, to embed skills and develop more suitable theories, support the practice of making clothing. So we need some way of kind of inverting it so that everybody has an opportunity to engage in some way with technology. And we see that a little bit more with some of the developments, mobile scanning, some of the applications that are coming are much more centered on greater accessibility for people, although there's a cost difficulty for people. But importantly, within the context of all of this, interdisciplinary work is essential for us to drive anything forward and for us to get any benefit from technology as well. So I'm going to talk initially about sizing, just to give some context. You see the title of this slide, the size of the problem, but as you've seen, from my perspective, sizing as it currently stands is a problem. Okay, prefaced on proportionality of a population, height and girth increase and decrease in a predictable manner. So lots of our sizing systems are predicated on this idea of proportionality in a population. And actually what the reality of it is quite different. And I think I won't go into too much detail. I would suggest you read Schofield and Labatt's papers, excellent papers from 2005. And they really identify grading practices, predate sizing systems. So what underpins our whole approach towards sizing of clothing isn't rooted in population data, because population data was captured after we developed grading and sizing. And so, you know, it's really important to then understand, well, what are the elements of sizing and how do they work operationally? So even when we look at limited dimensions of population, bust, waist and hip, they're too narrowly defined to ensure that fit optimization is met for the population. If we just look at how the bust, waist and hip measurements using the UK sizing match with the population, it's clear sizing is not suitably optimized for a population. So I'm just going to stop sharing this screen now. Forgot I was going to do that. I'm just going to skip to a different document, which I'll share with you all just to illustrate what I'm talking about, because I think it works better doing that. So what I'm going to share with you in a second is an Excel sheet containing anonymized population data. And it kind of illustrates the point of how sizing operates and some of the intrinsic problems in it in a way that is probably a little easier to do than some other factors. So this document here contains population data of an anonymized population with the bust, the waist, and the hip. Okay, and it shows them mapped against, we took this population in the context of it and mapped them to sizing data from UK retailers. And what we can see within it is that some people have lots of retailers they can go to and receive reasonable fit, and quite a lot of people have none. And if you go to the bottom, you can kind of see in this, and we're working here, this is quite important, we're working on a tolerance of fit, which says you're the size the retailer suggests you are, plus or minus 3 centimeters. So, you know, just over a natural grade increment for those measurements. And when we set this tolerance of 3 either side of those measurements, you can see that 86 of this 201 people, there is no size that they can be, that, you know, it means that the bust, the waist, and the hip dimensions of the retailers, even against that tolerance, they're not offered a garment that will fit them in an optimal way. So you can see 43% of this population against traditionally accepted tolerances of fit do not find good fit across the majority of UK women's wear retailers. So it's quite important to understand, but when you look at drop value differences and start to order people, say smallest to largest, this is difference between the measurements. You can see people have a small difference between bust and waist. They're left out here. And then you get into this majority of people, but even people here are left out for a variety of reasons. But you see a concentration when you go down to the other end of it. People with a large difference between bust and waist are equally left out with very limited numbers of retailers they might then fit within. So what I want you to take away from this is that current sizing systems leave a lot of people out. And some people may only have very limited, you see somebody here, 2 retailers. You see someone else 33. So what you end up with is narrow margins of the population with lots of opportunity to buy clothing, but lots of other people with much more limited opportunities. And sizing really just doesn't work in a way we would like it to. I'll stop sharing that and I'll try and now go back to the PowerPoint and pick that up. So where am I here? Share screen and go back to this. Okay. So let me just flip over and maybe go back one. So you saw that, but I talked about interdisciplinary work at the start, and that was done by a guy called Gerald Ruderman, who I've done a little bit of work with, but it's incredibly helpful. He set up the Excel document for me, but it's a really nice illustration of how the problems that sizing has. And I talked about it as an optimization problem. This is one of the ways in which sizing works. So sizing is a standard means of matching populations to products to achieve fit optimization. And we've seen it doesn't work well, but the dynamics of it matter. And optimization is really what it is. So if you are the measurements of the size, you will receive optimum fit. But the more that you deviate from the measurements of the size, the less optimal the fit will be for you. Okay, and we're talking about optimization against how the retailer anticipates the garment should fit and fit well. But essentially, we make lots of concessions in sizing every time we buy garments. And lots of the time, people will then turn that back upon themselves. You'll see there's a poll question here. We'll touch upon that after slide 6. Okay, but the key thing is a lot of the time, because sizing doesn't work effectively, it makes people feel that their body's the problem. And actually, really, it's the system by which we offer garments and the limited sort of scientific underpinnings of it. But what is sizing composed of? And it's quite important to get some clarity here. There are 3 main elements to sizing. There's the body measurements, and that's not just the body measurements it fits, because everywhere a garment fits over, it has a relationship to, there's a size dimension to it. So just saying, oh, we only deal with bust, waist, and hip, therefore this garment will fit more people, negates to actually identify the fact that if it fits over the upper torso, the shoulder width matters, the armhole matters, the bicep matter. So lots more data matter to it, but body measurements are an important component part of sizing. Another element of that is grade. And grade is the difference between one size and another, and it might be proportionate or disproportionate, but often they're similar. For bust, waist, and hip, there's a similar sized grade running through these here. But a lot of the time, people are guessing as to what happens with grading because, again, it's not rooted strictly in a population, and population data is very messy. But there's another element to sizing, which is important to consider, and that's drop values. So that's the absolute difference between the measurements of the bust, the waist, and the hip. The differences between those, and they matter. People say sizing doesn't exist, sorry, shape doesn't exist in sizing, but actually shape always exists in sizing. It's the drop values. The differences between those key dimensions are illustrative of the shape anticipation of the population that the retailer offers to. And when we go back to the document, I showed you the Excel document that Ruderman put together for me, that illustrates again, when you start to contend with shape and small or large differences between certain key measurements, lots more people are left out. So the shape offering is incredibly limited. So 3D body scanning, this allows us, within any limitations of the software, to perform detailed analysis on the body within a virtual environment. We can look at the body in much more detail, but you need a clear understanding of how measurement extraction and landmark placement works. We no longer, in this context, have a sort of physical contact to guide measurement placement using palpable features. So we can't palpate the body and feel for features. We instead got to rely on visual analysis of the body surface, and it means a new skill set has to be developed. What are we looking at? What might we identify, and how might we understand it? So I mentioned the question that was before. What I'm going to do is stop sharing now, because I think Christina has to share her screen for you to fill in the poll question. And then when I come back, I will go through the software before I pick up the presentation slides again. Christina, do you want to run that poll question now?
Yes, I will.
Yeah, so we're asking, using the same MERcon thing, I think, as before, are you personally happy with sizing optimization for garments you buy? Do they fit you well? So, answer yes if you think, what, I go into shops and it's dead easy. I can just get the garments I want and they fit me perfectly. Or no, if you go into shops, you pick several garments off. Sometimes you leave without finding something that fits you. Have a think about that. Christina, do we visit the answer now, or can we pick that up again at the end of my presentation?
It's up to you. Yeah.
Okay. Yeah. Well, I suppose for efficiency's sake, let's pick that up at the end when I've finished.
Okay. Yeah.
So I thank you for that, and everyone can use the link, I hope, to access that. So what I'll do now is I'm just going to share my screen when I talk about new skills. This is what the Sidestream software looks like. So this is an anonymized scan of somebody with narrow hips and a wide waist, which is one of the examples I'm going to use. But I want you to kind of understand what you might get out of it and some of the things you might look at. So it gives us a great opportunity to start to look at the body. So one of the things scanning technology will do is it lets us say, here's a circumference of the body. This is the waist circumference up here where my mouse cursor is. But it divides it. The scanner's saying this is a point that divides the arc of the front and the back. So what scanning does is it brings forward the time when we take a full dimension and distribute it. And similarly with the bust measurement, it says at the underarm point, this means, sorry, here, this is the front arc of the bust and this is the back arc of the bust. And it lets us understand those things. But it also lets us look at depths through the body. And it's quite important. So we can look at the seat depth, the depth from the front to the back of the body at the area where, say, trousers fit. But we can also look at widths as well. And when you think about the process of manually taking measurements, it has huge advantages using scanning technology because we can extract so much more information, more than we ever could. But we need to start to understand the scan differently. So if we look at this scan here, you can see there's a couple of points that represent the side neck. So I'm just going to make an adjustment as an illustration of some of the skills building you need to do with the software and some of the stuff we have to do with it as well. So I'm going to move the landmark for the side neck, largely because I want it to be in a position which I think is more appropriate. I think this is a little too far back. When we're looking at the side neck, we're looking at a point where the trapezius muscle, this muscle at the top of your shoulder, comes into the column of the neck, and just forward of that intersects with sternocleidomastoid muscles, which run down the side of the neck into the top of the rib cage. But they create an angular change, but there are some quite important styling elements of this. So when we look at it, we know that if this is the shoulder point, then we want a gradual slope back. So we know this side neck point probably wants to be about here from the perspective of a garment, but also from the perspective of the musculature of the body and what forms the side neck and creates this change. So we can actually move it in this environment, but we're having to develop a new skill of looking at this 3D body surface and then saying, well, what and where should these points be? And we can move both the left and the right neck points to positions we think are more suitable, and then we can store and process. So apart from the fact I can't change the physicality of this body in this environment, I can change how I analyze it, and I can take more measurements and different measurements. So scanning opens up this possibility to really explore bodies in a much more effective way. So I'm just going to stop sharing that now, and I'm going to go back to the presentation, which I should be able to do now. So if I share my screen with you, I'm back here from the current slide. Flip these over. This is all the stuff that should happen in the background, really, isn't it? Let's just get back to here. So I've been through this bit. We're just going to look now, the last bit, I'm going to talk about pattern automation. So it's something we've worked on quite a lot in the team, but it's built from scanning. We just can't do this automation without body scanning is the reality of it. It's incredibly difficult to make sure that you have a sufficient amount of information without body scanning to drive patterns effectively. But within pattern automation, variety of methods automate pattern drafting from manual or body scan data. And this isn't necessarily new. I can point out a PhD from 1986. They weren't using scanning technology, but they were automating pattern development. And I think it's always a surprise that we haven't automated it long before now, because actually it's very much a process of just laying points out in a very formulaic way. Automation speeds up the process, but it can enable us to gain more control over the pattern and its relationship to the body, and that's important. So one of the things ADE had done is we produced JBlock, open source pattern development software. Have a look at it, have a go with it. It's driven by the Sidestream scanner, but it allows for this opportunity to engage well. But the other thing we've looked at is new block development. So I have a number of researchers that work with us doing stuff on patterns. And what we found is that existing pattern making just really isn't great for getting control over and understanding what you do, not least of all because of the limited measurements that are input. So we have a number of these blocks, and we can look at suppression and shape and how proportions can be managed in them, which is quite different from how most pattern making methods work. And these parametric methods initially operate in Lectra Modaris. Why Lectra? And this is important. So JBlock is there, it's open source, you can access it. But Lectra is software that people in the industry use. And it has embedded within it tools, advanced tools in Lectra Expert, which allow you to build relationships between size charts and patterns so you can automate the development of a pattern. And we've done that in a number of cases. So we have the Aldrich blocks. If I want to create an Aldrich block, I won't draft it by hand. I won't even draft it in the system. I have a parametric draft. I'll just change the measurements in the chart. My draft will adjust. And then we can start to develop new ways of drafting as well. But it's important to use off-the-shelf technology because it's accessible. People have it and it's there in the marketplace. We don't need to develop things specifically for an endpoint. We can utilize things that exist. And I think that's incredibly important to make technology work. Let's leverage what's there before we look to develop things to replace it. So in the context of pattern automation, I looked at two individual people for this. it's about 3 hours work getting here. So I have two people here. One of them has a narrow hip side to side, but a deep seat front to back. And the other has a wide hip side to side relatively, but a shallow seat front to back. Key in these two individuals is they have the same circumferential measurement, well, a very similar circumferential measurement of the hip. They measure, one of them measures 101 centimeters, one of them measures 103. In the context of sizing, they're the same hip size for all intents and purposes of how sizing operates. But we can use pattern automation to create a block for them. So this is using a draft we have. So yes, there's a bit of changes that need to happen with the angle and smoothing through the crotch curve here. But what I want you to look at is this person who has a deeper seat has a deeper seat in the pattern, whereas this person has a shallower seat in the pattern, because that's what their body requires in terms of the shape of them. They don't need a deep seat for this person. It can be shallower. There's some other changes that I need to make to the pattern, but they're minor modifications to the outline shape that might arrive at something suitable. If we move to the next slide, so these are the bodies. This is a comparison between a traditional pattern draft using Aldrich's method, which is in blue, and the custom draft we've got here in a darker blue. So the cyan one is Aldrich's draft, but what you can't strictly see that exists is these Aldrich drafts, because the people have the same hip, they have very similar curves through the crotch here. But with this new novel draft, we've been able to modify the crotch curve to better suit the individual, but also it's distributed the shape effectively to replicate the body and the differences in the body as well. And that's quite important. So we don't have standard darts. They may be positioned in a standard way, but the size of the dart is dependent upon the size of the difference in the body. And that's quite important. So we don't have such regularized patterns from the custom draft, but it allows us to do some quite exciting things. So my last slide, a variety of research to improve how technology informs the pattern, conducted by a range of researchers. So there are distributed groups globally doing this. There's 3 references of people's work that I'm quite impressed by, and I think you should have a look at if you want to understand more. Than we're not the only people engaged in this, but it's important that there's some consolidation of the work that's happening, and the best elements of it can be built upon effectively and done so in a way that means it's accessible to practitioners, to ordinary people who would benefit from making clothing as well. So, you know, coordination of the work is important, but guided by the range of those involved as practitioners and solution developers. So trying to feed in and have that wider conversation. And that is my last slide. So I think, Christina, it's possible to touch upon the results of the presentation, and then if there's time, we can take a couple of questions. Yeah, so we kind of see from that, you know, nearly a third to a quarter of the population are happy, but the majority of people are unhappy with how sizing optimization works. And I think that's quite important to bear in mind that, you know, largely this is because the limited nature of the way in which sizing systems work and the way in which they're not grounded in real people's experience. It's why you often go to the changing room and take several garments in to try on, because that physical fit experience is important. And until we can find a way to both educate consumers, but also modify the industry, we may be able to find a mechanism to fit within. Often the industry says, we don't want to change, it's too costly. But if 75% of your population are unhappy with what you're offering, then I think the cost inversion is more important. We might make a lot more wasteful garments than we have. So I don't know if anyone has any questions specifically to what I've spoken about. If they want to drop them in the chat, Christina, or whether they were going to ask them, I'm happy to address questions now or at the end.
Yeah, I think we've got some time for questions. So if you've got any questions, just put them in the chat, please. I've put the link to the JBlock software in the chat because somebody asked for that, so you can access that.
Thank you. I've either spoken too fast or given too much information to everybody to take in, which is kind of fine either way. So, I mean, if there are any questions for me, feel free to drop them in the chat and I can answer them in the chat. But I'm happy, we can move on to the next presentation as well. Thank you. It was very nice to speak with everybody on that.
So, I mean, we actually just got a question in the chat now, if you can see that.
I can, yeah, and I'll answer that then before we wrap up. So, and I think this is a perception a lot of people have, which is that bespoke is great for made to measure. How can we relate to improving sizing for a ready-wear market? In its simplest terms, if we can make bespoke, then we can make mass produced, but they don't go the other way. We can't use mass production to increase bespoke, but we can use bespoke to better develop mass production. So for instance, people can do statistical analysis on population data if they want, but what matters is the resulting pattern that they get. So if we can understand how an individual body drives an individual pattern, then we can look at similarities between the two-dimensional pattern outline of a population, then we can create better sizing systems, because that better represents things. Like, for instance, in the sizing system, they never split the circumferences into back and front arcs. But the minute you start to draft a pattern, you take a full circumference measurement and put some in the front and some in the back. But you must do that in bespoke anyway, and you can then better understand the divisions of the body and how the dimensions break down. So if you can do made to measure well, then you can do ready to wear better. And I think that's the important thing. It's not saying it's a one or the other. It's about looking at ways to better inform people to make better decisions about practice. Angular data like shoulder slope. Yes, I think you can get a shoulder slope from it, but I think my recommendation would be just to look at drop. So what's the physical dimensional difference in space as a dimension between the side neck point and the shoulder point, and look at that as a drop, because we can relate to that much more effectively. We can look at slope. It's harder to define. It's sometimes a bit harder to work with as an angle. Definitely no pattern says draw X at this angle. It says drop this shoulder point this much. So we can look at drop, but I think there's very little you can't get out of scanning data, in terms of the analysis is possible. There's so much opportunity there. Available data sets, not of scans, but I think we've got 100 scans we can share that are just the extracted data from 100 scans that are available as a link somewhere. So you can look at what those measurements mean. Sizing and fabric materials that affect the garment fit, woven and stretch, woven structure. I think maybe that intimates a little bit that what people often do is they say the fabric stretches, therefore the fit is easier. But what I would say is there's still optimization effects there. And so even though someone might more easily get into a stretch garment, they're not then achieving optimization. It doesn't really fit. And you see that sometimes through garments which are stretched so tight on a body, they're almost sheer. The person's fitted into them, but they're not optimized well for them because they don't serve them aesthetically. So there's even with stretch, even with knitted product, there's still an optimization element to it there. I'm prepared to accept there might be a greater tolerance of fit, but I'm not prepared to, to move away from the idea of optimization that still should be achieved there as well. It's not a panacea to say stretch will just make it okay. I think we've probably covered most of the questions, Christina, so we should probably move to the next one. But thank you everyone for the questions. And it was very nice to have the opportunity to speak with you all.
Yeah, thank you very much, Simeon. That's great. And I'm sure if you've got any more questions, Simeon might be able to answer them in the chat as well. Okay, so that brings us on to part 3 of our workshop, and that's 3D CAD modeling for virtual prototyping applications. And if you in Sri Lanka will be familiar with her from the University of Maratua. And yeah, over to you, Jo Mali. I'll stop sharing.
Thank you, Christine, and thank you, Dr. Simeon, for your wonderful presentation and explanation of all the questions that are asked from the audience. Let me share my screen. Can you all see my screen?
Yes, we can.
Yes.
Okay, I will hide my video to improve the clarity because of the network connection. Okay. Out of 4 objectives of the workshop, I will include my input to cover the second objective, as Christine explained you the session outcomes. I will briefly explain you what is virtual prototyping, and I will show you the application of 3D CAD tool to the process of virtual prototyping in the context of apparel. I will show you some of the tips to improve you to have the true to life nature of 3D clothing simulation. And for that, I will use my own video to demonstrate to you the 3D CAD tool, which I am going to use for the day. And of course, because some of the participants, they are not familiar with this 3D tool. So then I will discuss how physical parameters of the fabrics affect the virtual cloth. And finally, let's discuss the future developments which demands from 3D CAD tools. Let's see the motivation to learn the virtual prototyping in the context of apparel. I think you know Gartner's Hype Cycle for Digital Workspace 2020. In this Gartner's predictions, the virtual prototyping strategies are the essential tools to ignite the conversations of the digital transformations in the apparel industry. And we can link virtual prototyping to have the smart workspace and workstream collaborations and the virtual events. So, and also the industrialist who connects today, they know the industry buzzword we use these days, digital transformation, because it has become the one of the key strategies in the present apparel industry. And creating the virtual factory is the future vision and the dream of ours. According to the latest reports in the industry updates, the 3D CAD technology was a lifeline in the past year during the COVID pandemic. Virtual prototyping has become the new catchphrase of the industries across the globe. With digital transformation happening in the new product development of apparel, 3D CAD technologies opens a new door to simulate products and process and control their operations and working. Yes, virtual prototyping. 3D software has been effectively used in engineering and industrial design processes, where design concepts and ideas can be presented with low cost, detailed 3D virtual prototyping to aid the visualizations of alternative solutions. Therefore, we could establish and accelerate the communications, assessments, and decisions. Virtual prototype is a computer simulation of a physical product that can be tested through design to manufacturing cycle. The taking decisions on physical prototypes, we would use virtual prototype tools to have enormous benefits in terms of computational design and simulation environments. As a result of that, pattern makers are now capable of solving 2D CAD patterns digitally by selecting the segments on the pattern pieces that will be connected together, positioning the digitally stitched patterns around 3D body forms, and running the simulations to create 3D virtual prototypes. 3D virtual prototypes allows us to understand how the product would look in reality and is useful in the early stages of product development. Yes, let's see how 3D CAD encapsulate into future apparel business. I will use this slide to explain the role of 3D clothing simulation in apparel design to product development activities. In conceptualized stage, the future designers and the marketeers can demonstrate conceptualized products using digital tools. Before products display on the market, designers and marketeers can play how to available proof of concept demonstrations in the online platforms. In conceptualization stage, it can simulate more design iterations, helps visualize initial ideas without wasting physical resources. Virtual prototyping would be the very effective platform in collaborative product development. In the industry, on average, sample approval process takes around 2 to 3 weeks. So it will have more like a high lead time. So then the situation even worse when the sample is rejected. Then product development teams has to go through again the sample iterations again and again. I think you may have experienced during the COVID period how the application of 3D CAD impact your business, because during COVID, the 3D CAD applications has been exponentially increased. You may have records that how many styles you have been processed through virtual fit approval process when compared before COVID time. In this case, obviously, virtual prototyping can be used effectively in collaborative platform within the relevant value stream partners and can enhance product development activities. Let's see how virtual prototyping can be used in co-creation, customer co-creation platforms. Customer and the product developer integrated product development models are demanded in the industry now. Customers and developers can interactively influence the future of a business product, including their product design ideas and manufacturing methods by using virtual prototyping in early stages of the product design. Simulate. Yes, there are multiple design ideas can be simulated in this virtual space. Product developers can test different fabric ideas, trim embellishment ideas, and the placements, and they can assess the work in the virtual space. Process, and let's see how they compare, because process, only the physical prototype is costly process. So 3D virtual prototyping can minimize the time and cost spent for digital design iterations by reducing the number of physical samples for each garment before mass production. I think in the statistics say we can reduce 3 to 5 samples to only two samples according to the statistics. However, after fit samples, the organizations have their own SOPs to compare the physical samples against the virtual creation. Today, I will explain you the analysis part, how we use this virtual prototype and the analysis and the fit analysis activity, because I will explain how this tool can be used for fit evaluation and for further analysis. These 3D CAD tools are not open source resources. So these companies, they release their own licensed product to use for virtual prototyping. If the industry people, they know these brands and they supply those solutions for 3D CAD clothing simulation. Simulating a garment does not mean just scanning. I would say it is a theoretical simulation based on the mathematical models of color, fabric, and constructed garment components draped over the avatar. Right from product development, these virtual copies give control over the product or process from the design phase of the development phase. This slide explains the basic workflow which we follow in V-Stitcher, because here I use the brand V-Stitcher because that is the brand available at the Department of Textile in our university. So in V-Stitcher, we export DXF file, or else it has been the total facility to create the patterns on the screen. However, patterns need to be created according to the correct body measurements as explained by the Simeons in his presentation as well. And then we have to assign the grading rules appropriately. Virtual fit models can be either parametric models or generated from 3D body scan data. Or then pieces need to be arranged in the right body placements. During or after preparing 2D patterns, users can assign materials. And then to create the realistic effects, we're supposed to map the real material types and the 3D trims and the transparency and the scaling and the other texture of the materials. After that, pieces need to be prepared on the 3D avatar, need to stitch correctly. In stitching, the user needs the knowledge of garment constructions, joining patterns, and the edge constructions and the attaching components. Then we dress, that means simulate the virtual garment on the virtual avatar. In assessing the technical fit, there are pressure and tension maps inbuilt in the tool. Importantly, if we use these virtual products to promote the promotion process, we need to apply the right 3D environments and lighting conditions. Developing 3D virtual prototypes requires certain skills and dedication of time. It involves a reasoning process through processing virtual information, creativity, and decision making. On top of that, it needs a knowledge in physics or physical properties of the material when you work with new fabric types. I will play a small demonstration referring a very simple garment for you, because if some of you are not familiar with this V-Stitcher tool, I think it will help for you to understand how it works.
When you open the V-Stitcher application to the screen, this is the interface you receive.
Can you hear the sounds, please?
Maybe not this.
Yes, Anna, we can hear.
Okay, good.
The avatar can be selected according to the product category and the shape you require. I will use a simple garment to this demonstration to show you the basic workflow. Let me open the pattern pieces to the screen. In V-Stitcher, you can import the DXF format of pattern pieces, or you can create the pattern pieces on the V-Stitcher software itself. On your left-hand side, you can see the Resource tab. You can see the relevant pattern pieces to the style. And then here you can see the materials that you are planning to use to this garment. And here you can see the seam types and the artworks and the trim accessories. And here in the libraries, V-Stitcher browse where available existing materials for you to use. This is a 2D window. Obviously, you can see all the 2D pattern pieces which you are going to use in this style. This is a 3D window, the 3D garments and the avatar. Let's go to the Arrange mode. In the main toolbar, Arrange mode is used to arrange the pattern pieces in the correct place of the avatar. When sleeve drags to the sleeve cluster, then the other side is automatically moves, and because those pieces set as symmetrical. If the pieces are non-flat, then we make this as constraint area. Then the neckband will have the closed piece, and it will render in the 3D avatar correctly. Then let's move to the prepare mode. Then prepare mode is used to arrange the pattern pieces on the 3D avatar correctly. Adjust the pattern pieces. We can adjust the pattern pieces in the 3D window. Then use main toolbar, switch to stitch the garments to the required assembly construction. Let's start stitching. We can stitch the shoulder seam and then the side seam to the side seam. Then the other side is automatically stitched because these pattern pieces are symmetrical. Then let's stitch the underarm sleeve and then use multi-stitch feature to stitch the armhole and the neckline curve. Start stitching the front and the back of the t-shirt to the armhole curve and then press done. And then let's start stitching the neckband using the multi-stitch feature. When you open the restitcher application, let's press the garment. Now you can see the garment is stitched properly and it has wrapped onto the body. And then we can get the fabric library because if you need to change the material, so you can select the material accordingly. Let's get this French terry. We can change the color of the material. We can assign this material. And if you want to change this color as well, if you want to change the rib color, if you want to change the physics of the material, then you can get the physics and change the mass of the fabric, friction, thickness, bend, stretch, and all the other parameters according to the requirement. You can get the colorways from here. Because these colors and all the other attachments you can link to the text pack.
Okay. Okay, let's come back to the presentation. And then let me ask you, as consumers, what is your expectation according to the literature? So these are the main expectations we record from the customers: the fit of the garment, comfort, functionality, and the aesthetic. In this presentation, using the 3D CAD tool, we concentrate only the fit, functionality, and the aesthetic, because still we don't have the mechanism to measure the comfort of the garment using the 3D CAD tools. This is technical perspective of the 3D clothing simulation. And here, this is the management perspective of the 3D clothing simulation techniques. Okay, under this fit and function, we need to correctly input the fabric physics, need to assess the pressure and tension maps based on the posture movements. And as I mentioned you, the body measurements are most critical factor when assessing the fit. Under aesthetics, we need to define correct wrap types, correct fabric aesthetics, including the material texture, to achieve the true-to-life virtual fit. Finally, as I mentioned before, you need to include the required lighting condition and the virtual environment. These are the key fabric parameters we need to consider in this 3D clothing simulation. This working is important to fabric technologies. That's why I have included it here. In fabric technologies can work together with the garment development team. Then FabTech, that means fabric technologies, will be able to source more appropriate materials according to the garment end use. You can watch this video of the fabric analyzer. And then you can understand how it helps to get the required parameter to the V-Stitcher software.
We're saying goodbye to manual fabric analysis and complicated data entry, and hello to the digital age with the Fabric Analyzer by Browseware. The Fabric Analyzer identifies the thickness, stretch, and bend properties of any fabric for visualizing garments. Simply place your fabric on the machine and retrieve the data as you work. Once analyzed, the property values can be automatically loaded into 3D software programs like V-Stitcher for true-to-life 3D simulation of any pattern with any fabric. For more information or to schedule a demo, visit us online at browseware.com.
Yes, let's discuss these fabric parameters one by one using the next slide. Mass of the material, the mass of the fabric measured in grams per square meter. So if we have the fabric analyzer tool, then we can directly import these measurements to the 3D CAD system, or else we have the fabric library inbuilt with the 3D CAD tool, so we can get those materials from the 3D software. Coefficient of friction measures the amount of the fabric resist sliding on the avatar. Then that value lower, that means it's easier for the fabric to slide on the virtual avatar. The higher the value, the more the fabric will hold its position. We need to know these parameters when we do sportswear manufacturing, so to the bottom band and the shoulder straps and all. When we map the real material characteristics, so we have to have the idea on these fabric parameters accurately. Then let's see the thickness of the fabric in millimeters. We're supposed to input it here. And then the bending rigidity, that means the stiffness of the material measured in dynes per centimeter along with the width of the width and the length. The lower the value, that means the less stiff the material. The higher the value, the less the fabric bends. For an example, in apparel clothing industry, we use the leather like the leather, and some denims are the more stiff materials. It has thousands of value when we consider bending rigidity. Then the tensile stiffness, or we call stretch of the fabric measured in newtons per meter. along the width and length wise. This property is the amount of force per unit of length needed to stretch the piece of the material to twice its length. If the stretch value is lower, that means the fabric is more stretchy. Then we'll see what is the stretch linearity. When stretching the material, it sometimes the fabric is easy to stretch at the beginning, then it becomes more harder. Sometimes it is the other way around. The higher the value, that means again the more friction, more fabric can be stretched at the beginning and until the material's resistance stops the stretching. In general, in the apparel manufacturing, the product development, the elastic has higher linearity and knitted fabrics have intermediate values, and obviously the woven materials have low values. And then the shear rigidity is the stretch of the bias direction, the amount of force measured in newtons per meter again, along with width and length wise. And then this amount by the fabric shrinks, and here is again the fabric shrinkage and values. Again, we need to input the lengthwise, widthwise shrink value. And then the puffy firmness, it applies in the like a jackets for like a to have the more resilience. And then the molded parameter we use in the bra manufacturing. Then in the prepare mode, we can see how it looks like on the body. Let's compare these outfits, because in the left hand side, in the solid color one, which I have created using one single material, where I will compare against the sports outfit which was made out of different materials. Here I have assigned the different fabric physics to these panels and assess the tension map. Tension map and the pressure map are the assessment tools we used in the 3D CAD system. Let me explain this tension map. Tension map is like the color-coded map on the garment showing the tension in each part of the garment based on the physics of the material. White means here you can see in the like white color, that means it no tension, and red means the most tension. And pop-up menu, when we get the simulation done, and then pop-up menu defining these color values in grams per square meter. Then the pressure map is a color-coded map again. It's a garment showing how tight the garment is on the body of the avatar. Again, the white means no pressure and red means the most pressure. Again, when we get this pressure map, and then we can see the values are in grams per square meter. Here I have done some posture movements, because this information is needed for the garment technologies to assess the fit on with the functionality. And then here, because garment technologies have to assess the garment fit in the several body areas, in the several landmarks of the body against this pressure and tension maps. Yeah, I will use this. Here, this I have presently in a graph, because in this yoga warrior, because these are some of the postures we assess. For that previous experiment, I have used these body postures, and then the here I have put this tension grams per centimeter value, and we can see in these postures how these tension values react. Here I will use this video to show you how these pressure tension maps here. In the 3D window, we can get these different postures, and then you can see while moving the body, you can see how the tension values are changing. This information is needed for pattern technologies, because if they are more on compression clothing and the sports wear and the foundation garments manufacturing, they need to know these believes this information is very useful to the pattern engineers. So they should have the understanding of biomechanics. I mean, when they do sports clothing, need to select correct sizes of the avatar to compatible with the pattern pieces, and also need to apply accurate ease allowance, and also need to grade the patterns correct for the correct sizes. Here, I have used this slide to show you what are the aesthetics we can include to this 3D clothing. Similar to 2D CAD tools, so we can include all the styling details, patterns, darts, and all the other fullness, values, fullness, styling appearance to these virtual avatar. And here I will show you how after we simulate with the correct material properties and the correct correct trims, accessories, placements, and all, finally we can have the animation of to assess the functionality of the garment. Let me run this animation as well. Okay. These are some of the examples of applied correct lighting and 3D environments. Because we can use these images for the promotion, because those days we have dispatched salesman samples to do all the promotions by the customer, the retailer side. So in here, after we have done like all fine tuning and applying the correct 3D environments and the lighting conditions, we can use them for the promotion purposes. I think it is more useful when in online retailing market to promote the products prior to do all physical product make. Yes, let's see the future of these 3D CAD tools. When we discuss the future demands of such tool, current research and developments are focusing to replace the hard surface avatar with soft tissue avatar, because the research and developments are going on to have to replace the virtual, because the still the textile, because those are very sensitive materials having so many parameters, but still the mannequin, the surface is hard. So we have to assess to get the correct predictions of the fit and constructions and the final functionality, we'll have to have the soft tissue avatar. And let me discuss again the future developments, because in the future developments, we'll have to replicate and we'll have to showcase the performance aspects of the digital garments as well. So, and also we have to, because currently we do some research on how the fabric physics render on the virtual garment, and how all those parameters are changing, how the tension and pressure maps react. According to that, we can analyze the sensitivity of the 3D CAD software as well, and then we can get more decisions prior to do the physical product. And then yes, when we talk about the future developments, yes, the number one, the soft tissue avatar is demanded, and also in the process wise, when we relate these tools to the business process modeling, so that we have to, because these software systems work as an isolated system, isolated tool, so we'll have to think about the integrity, how to integrate these tools with the rest of the value stream activities. So that's why I'm here. I mean to integrate these systems with the PLM systems will be more benefited, and also we can use these tools as for the e-commerce platforms. And also currently there are research, and also in my PhD dissertation also I suggest to enhance these tools with the AR and VR applications, because AR is currently widely available as mobile devices, and creates interface that explore new ways of interactions between the actual and virtual world at the same time. So I think let's see the more in future what we can do with this virtual prototyping, enabling in these AR and VR environments. And also, finally, I would like to say, because the tools are establishing and tools are available in the market and in the business, but we have to think about how are we utilizing these tools effectively. That's why, as an academic, as in the educator in the field, I would recommend to have the more like to the teaching, because we have to include these in our education, our curriculums, and so that in also, especially when we teach pattern making, we require the use of these 3D garment simulations. So we'll see how to have the more training and developments in the industrialist. Okay, now this is the end of my session, and Christine, over to you.
Okay, thank you, Jayamali. Did you want me to run the poll questions for you now? Or?
Yes, please, Christine.
Yes. Okay, no problem. Okay, so this is again using the same session link to the poll. So we've got the response.eu and still the same session, MERcon 21. If you could just quickly answer these questions. Is your organization currently using 3D CAD software?
Industry participants, you can respond to this question. Is your organization currently using 3D CAD software in virtual prototyping?
A few yeses, quite a few yeses. So people are. Poll says. So here in the poll, we've got a mix, so we've got 64%. So yes, they're using them. Okay, so then the next question is, are you a 3D CAD user and virtual prototyping for apparel? Okay, so you've got a few answers in the chat, Jamali, saying no. So obviously their organizations are using it, but they personally aren't the 3D CAD users. So maybe you could let us know what role.
Yes, there's a question is asking that vStitcher output is that compatible with the other 3D CAD tool, with 3D CAD files, because we can use like in 2D pattern conversions, DXF is the common file format. And also, yes, because these days the software solutions are promoting these compatibilities and the convertibility, because that is how, because it not like those days, because those days like they market one product and then the only like a very few products that was in the available in the market. So I think they have the convertibility facility.
Okay, yes, I've moved on the slide already in the meantime, almost to answer the question, and we're getting some responses in them. How many years you've been involved in 3D CAD if you're a user? Okay. Oops. Okay, so mix of experiences here. And then you've got another question there, Jamali, in which product category do you use 3D CAD? Lots of people responding in the chat saying casual wear. Someone also said swimwear and sportswear, which is interesting. Intimates. Okay. Okay, so we've got here intimates and sportswear.
We have the balance audience that they are using like a diversified products, and also the diversified audience, some are like user, 3D CAD users. Let's go to the next question, Christine. I think it's the last question.
What is your motivation for using 3D CAD and virtual prototyping of apparel? All three. Someone said in the chat. If it's any other, let us know what the other is in the chat. We'd like to hear that. Okay, so. Okay, you can see here on the poll, we've got the majority set digitalization strategy of the organization.
Yes.
Okay, that's great. Thank you very much, Jayamali. That was very interesting. And yeah, just in terms of, I'm conscious of time. So if you've got some questions, you can put them in the chat and maybe Jayamali can respond in the chat to them, yeah? So let's move on to part 4 then of our workshop. So this will be presented by Dr. Ranga Surya. It's about digital technology for cutting and packing 2D shapes. So I'll hand over to you, Ranga.
Okay, good day to all of you. I'm going to conduct the part 3. So after having 2 nice talks, so let's move on to the part 3 now. So yes, this is our scope. We were talking about product development, and so we were talking about the importance of product sketches, the body anthropometry, and then we're using these two, we created the pattern pieces in 2D, and then these 2D patterns ultimately will be transferred or assembled into a final 3D product. That's what we call it as garments. But when it comes to the product development to the manufacturing, so it's all about the developed products, and we need to make the copies of it. So that's what you basically identify as the manufacturing. So in terms of manufacturing, yes, we need to deal with a lot of garment pieces, garments. Ultimately, it will be handling of a lot of packing pieces like this. So when it comes to the garment assembly, so the major input will be the cut panels, and you need to cut those panels from the fabric stock sheets you have. So this is what you basically see. And when it comes to the scope of my talk, basically I'll be touching about the packing pieces area, as well as the developing the cut template layouts to have the panel pieces. So those are the 2 areas that I'll be focusing. And if you look at in a high level of the process within this scope, basically this is what manufacturers sees. So when it comes to the packing pieces, they see them through the packing engineered softwares. And then when it comes to the cut plan or the cut layouts, they see them through the cut plan optimizers, or maybe as waste minimizing optimizers. If we go one layer down, or in other words, if we go a little bit in detail, so if you look at in the developer's perspective, of these different tools. So they see these things as digitizing and visualizing irregular shape polygons. So we call these pattern pieces, how they see them as regular shape polygons. And the same thing, so when it comes to the cut plan optimization part, so they see those things as mathematical models of optimizing cut layouts, or maybe optimizing the resources. So that's what you see in one layer. So when we further go down another layer, so if you look at from a mathematician's view, or maybe a computer scientist view, so for them, they look at this as the application of computational geometry, or it could be computer vision. And when it comes to the other side, in the manufacturing part, so it's all about application of cutting and packing algorithms. So usually we call them as cutting and packing heuristics. And you can see that some meta-heuristic approaches are there, or also as some exact algorithms such as mixed integer programming approaches. So that's what the things that you see when you are working in the core part of these different applications. So having that introduction, I am moving to the outline of today's talk. So then we will have a discussion about generating 2D cut templates. And then we will discuss about what are the background concepts behind these 2D cut templates. So I'll be focusing more about the computational geometric concepts applied in digitalized patterns and the visualization part of those patterns, because that's what obviously you see in these digitalized applications. And finally, so it's about how to optimize the cut template layout as well. So because we usually, I use the word the cut template layout. So if you are from the industry, the apparel industry, we basically call them as markers. So I'll be thinking about talking about how to optimize the markers and what are the different optimization approaches available to deal with these kind of problems. So in fact, so in the process of generating an optimized cut template, so these are the steps you probably follow. So the first thing is if you want to do it by your own way, so then first you need to think of like how to feed your 2D patterns into a computer. And then you need to think of like how to place those patterns in a cut template layout or on a marker. And then finally, you can think of like how to optimize those things, those placements in order to achieve a high utilization of fabric, or maybe reducing the waste as much as possible. So then, so when it comes to 2D patterns, so then if you really want to work in this area, so you need to consider them as irregular or regular shaped pieces, or in other words, it's all about polygons. So you are basically dealing with the polygons. Those are the geometric shapes that we have to be interested on. And if I be precise, so so then it must be polygons with holes. And then, so why the computational geometry is important? Because since you have to play with the polygons, so when you are making this cut template layout, so basically you need to translate polygons from one place to another, or else you need to rotate the polygon from one angle to another angle. Sometimes you will see some overlappings will happen in the polygon. So again, that polygons, so the overlapping part you need to control. And sometimes you need to keep some buffers in between the polygons. And sometimes you have matching requirement to be achieved. And also sometimes you have to enlarge those polygons, because we are dealing with flexible material. So the fabric shrinkages, stretches could be happen. So again, we need to have some inputs from the fabric physics, and then accordingly we need to control the polygon shapes and the polygon sizes. So then it's very important to bring the concepts of computational geometry into action and reach the accuracy of layout as much as possible. And when it comes to the optimization side, it's about optimizing the cut templates. So yes, so while achieving accuracy, so we need to think about reducing the waste as well. And when you're trying to reducing the waste, yes, you can run the optimization algorithms for a longer time. But the problem is, one limitation we will have is the computational time that it takes to see a good solution, or maybe the optimized solution. So in that sense, so we need to think of efficient cutting and packing algorithms to make this whole process to a real efficient one. So digitizing packing is indeed challenging. So we are talking about really irregular packing sheet pieces. So they can be either convex or non-convex polygons. And the other problem is the garments packings are. So we have to deal with large number of vertices. It's not like dealing with very small number of polygons with a very small number of vertices, because we have really sharp curves. So when you have curves, so you have to allocate more vertices, and then ultimately you have to deal with a lot of very large number of vertices. And then, so depending on the material characteristics, so you may think of like rotating pieces, sometimes to a finite angle, like 180 degrees or sometimes 90 degrees, but sometimes if you are working with a really homogeneous material, so then you can think of like allowing pieces to be rotated freely as well. So yes, indeed, in a large production environment, so we have to deal with higher number of pieces, and they are really heterogeneous in sizes and shapes. And then we have extra requirement like curve shapes, and on top of that, sometimes, especially when it comes to the intimate wear, so then we have really small packing pieces, and then we have really sharp curves, and which we need exact shape as it is to get the required fit of the garment. So then dealing with this kind of complicated and complex environment or complex polygons would be a really critical thing. And indeed, the quality of graphics and the quality of placement, the accuracy of the polygon geometries is very important. The second part is about the optimizing the cut template. That is even more challenging, because if you are a person who works in the operational research area, you will simply say this as hard. This is two-dimensional irregular packing problem. But by knowing about irregular packing systems, they will understand how hard this is, because the mathematicians define this problem as an NP-hard problem. If you are a mathematician, you will understand what is the meaning of the NP-hard problem, as well as how hard to achieve and optimize. I mean, optimizing this is achieving a solution, the best out of best solution will be really challenging if you are working with this area. So as I told you, so we have to come up with very good algorithm, and then so the real problem here is like the computational time that it will take, because when it comes to the industry arena, so the real operational scenario, how the time it takes will be a matter, as well as the time it allows you to have or see a solution. The time they give to see a solution will be really limited. So then in that context, thinking about optimization algorithm will be a really challenging task. And so if I say about this irregular shape packing problem, so as literature says, it's still a very hard problem to solve. And there's a limited, there are a lot of limitations from the computational time aspect. And usually, if you want to find out an optimal solution for 5 complex pieces, sometimes it would take more than 6 hours if you are using exact mathematical models. Exact mathematical models are like the mathematical models like mixed integer programming models, because they are seeking the best out of best. So that's how the nature goes. So many commercial softwares struggles to reach these targets, and due to that reason, so they are heavily dependent on many heuristic and meta-heuristic algorithms. If you see almost all the commercial software available, they are heavily dependent on the heuristics and meta-heuristic algorithms, which they find good solution, but not the best out of best. Yes, so when it comes to the packing algorithm part, so in terms of geometrical shapes, I will discuss all these things in detail with the next few of slides. So what we can see is like in the naked eye, you will sometimes easily understand whether two pieces are overlapped or whether two pieces are touched in a cut template layout. But sometimes when you zoom in, so when you enlarge it, so you will find there could be some tiny overlap, or maybe some polygons are enclosed with another one. So if that kind of thing happens, so then it will become a problem. So that's why, so this geometric programming constraints are really critical when you are dealing with this kind of problem. And then if you are a programmer or if you are an optimizer, so then you need to be pay attention on these kind of geometric constraints available with this problem. So as for example, I told you about piece buffers, piece rotations, sometimes pieces can be flipped, piece scaling, and handling the tolerances. It's really a critical task if you really want to do a programming task in this particular area. So now this part I will discuss with some practical examples, how if you really want to get into this task. So from where should I start? So what are the supporting aids I have? So let me explain you about that a little. So the first thing is, if you want to develop a cut template layout, right? First thing is you have to think of in a programming aspect. So you have to think of how to represent your pieces, because you have regular pieces. So then, so you can either represent them in a computer using discretized methods, or maybe non-discretized methods. So one common discretized method is like pixel raster method. They are really simple to code. If you want to represent your pieces like this, so it's very simple to code, and the algorithms are fast, but they will be really memory intensive. And the other thing is that cannot exactly represent the orthogonal edges in the piece. So you can, as you can see in this the pictures, so you see the difference between the raster one and the vector graphics, right? So, and even here, you can see that one. So now I'm talking about the accuracy. I'm talking about the technical requirements of having some sharp curves. So then if you go with this method, so then you will face some problems. So that's why in fact, I am a fan of this non-discretized methods, and I am usually working with the vertices where you have the facility of using the polygon as it is directly. And then, so your information will be more or less the vertices. And then you are talking about a vectorized representation. This will be computationally complex, but you have the comfort of reaching the accuracy. So that's about how to represent it. And then what are the supporting aids I would have? So yes, we are going to deal with these basic geometries like points, lines, polygons. So if you really want to get into this area, so I recommend you to have a look on these open source geometric libraries available. So they are more or less computational geometric libraries. So the Boost Geometry C++ is one, and Seagull is one. And also, so if you want, you can have your own one as well. If you really understand the concepts and if you know the basic concept of geometry, and if you have some idea about computer programming, so you can develop your own set of libraries as well to work with this area. So that's the beauty of this area. And then, so it's a matter of generating the other operations, so which you can also use your own libraries if you want, or else you can use the inbuilt libraries like Boost C++ or Seagull to do these kind of operation, like finding the distances, finding the area, translating the polygons, rotating the geometries, simplify the polygons. I will go one by one and show you how it's going to work. And the most important thing is these auxiliary features as well, because so we are not always try to feed the polygons manually to our computer, because since as the previous two speakers mentioned, so we have some softwares. So then if you really want to get into this area, what you can do is you can think of like making your own libraries, or maybe using this Boost C++ or Seagull to match with or to integrate with the other available softwares as well. So then if you have a code, so which I used in this particular format. So if you have a code to convert your DSFX files to SVG files, or maybe your DSF files, so this must be DSF files to boost polygons, or maybe that will be really benefited because you can easily connect with the available tools as well. So ultimately your program will be based mainly integrated with the available tools. The other part of it, like the visualization with vector graphic formats, that is very important because if you want to enlarge them and if you want to see the real accurate shapes, so this working with this format will be really useful. Okay, here I'm going to discuss one example. So if you want to have a packing layout, or say for example, cut template layout, or simply a marker, right? So first you need to feed the polygons that you have, or feed the pieces you have. So I am here explaining one application, one example that I used using the Boost Geometry library. Okay, and here, so these are the steps. So you can easily call the basic components like points, lines, polygons, multi-points, multi-lines, multi-polygons, following these set of codes. So, and then this is about the calling libraries. And then you can define and declare your polygons properly. So say for example, here I am defining a polygon having 81 vertices. So you can see the coordinates I am feeding here. And then ultimately you can feed that one. And later on, if you want, you can visualize it in a SVG format like this. So this way you can simply feed a polygon, right? So then if you have several polygons, so you can create an array of polygons and then you can load them into your computer, and then you can keep it. Then you can use that one in the next stage. Right. So in the process of making cut template layout, so after having an array of polygons, so probably you may need to move those polygons. So then if you want to move those polygons by a certain coordinate, you can apply this translate function in the Boost Geometry easily. And then you can move that polygon from one location to another location, right? So in this case, this is the one I am using. Similarly, if you want to rotate the polygon, say for example, this was the original polygon and then I wanted to rotate it by 45 degrees. So then it was rotated. So then by applying this rotate transformer function, and then you can basically rotate the polygons to a certain angle. And then, what else you can do is, so say for example, now if you want to make a cut template layout, right? So I'm going to show you how it starts. First, so you are working with a certain worksheet or a stock sheet. So this could be your fabric ply, where this could be your fabric width. First, you can simply position your first polygon like this, okay? And when you want to place the next polygon, so what we should know is the next polygon should not be overlapped with the first one. And also that polygon should not exceed the boundaries of the stock sheet as well. So then how to achieve that one? So if you want to find out the feasible locations that this particular polygon can be placed, so the way of approaching is, so in the computational geometry, there's a concept called Norfolk polygon, right? So when you calculate the Norfolk polygon between these two pieces or the polygons, so this is the Norfolk polygon that I derived using some of the algorithms that we have from our research group, right? So then what happens is like you will be able to find out this Norfolk polygon, and then what we are interested about is this outer boundary of it, or the edge of those polygons. So any edge of that, any point on that edge will be a feasible position for you to locate the second piece. When you locate it like that manner, it will not be overlapped. It just touches the boundary of that one. So that way you have some finding of where to be located. And the second thing is, so we know that, so we have to place that second polygon inside the rectangular worksheet, sorry, the stock sheet as well. So in that case, so we have another concept called inner fit polygon. So first one was the outer fit polygon. The second one we call it as inner fit polygon. So the inner fit polygon, so basically find out the feasible location points where you can place this second polygon inside this worksheet without overlapping with it. So basically it will determine the enclosing feasible points. Okay, so now when you take about these two regions and get the intersection, so I mean the region in the sense, the first region is about the boundary of this morphic polygon, the first one, and then the boundary of the inner fit polygon. If you get the intersection, in fact, that will be the feasible region to be placed. So this second polygon. So in fact, this line here highlighted in dark. So any point on this particular line can be considered as a feasible placement position for the second polygon. So likewise, so the overlapping matter and the enclosing matter can be solved by using the computational geometry. And in this particular case, we are using the algorithm developed by Ben and Langsong in 2008. So the algorithm is about generating orphic polygons based on the Minkowski sum approach. So if you are a mathematician, you may know about the Minkowski sum approach, and that is one approach heavily used in computational geometry as well as some other automation applications as well. So basically, what happens is, so what we are doing is so we are using this packing algorithm so to put the second piece, and then you can have a second piece like this. This is another example. But similarly, when you want to go to the when you want to place the third piece, the approach will be like you have to consider the first and second pieces together. So then it will be like a union of the previous two polygons. So then when you are placing a third piece, basically you consider the original piece as this those two pieces, and then follow up the same procedure. So in that case, if you want to do that kind of thing, so yes, indeed, you need to think of like how to join two polygons. So how to get the union of two polygons. So if you want to get the union of two polygons, you can use Boo's geometry libraries, something like union. And then you can see here, I made so that these two polygons were initially I have, and then I translated closer. And then if it is touch, it's possible to have a union of this one. If you further translated this or move this further, so you can see like still you can get the union of it, but it will be having a sort of problem here. And the other than that, the Boost geometry library, even if you see this kind of scenario, if you want to get the intersection point, in some case, maybe if you want to look at, or if you have an interest on this intersection point, you can give out that part only, or else you can cut off that one by applying the difference function in the Boost geometric library. So that kind of operations are possible with these computational geometric areas, and it is highly used in this kind of applications. And how about this one? So I am pretty much sure this looks really interesting for you as well. So this is the same piece I was talking about. It's just 82 pieces. And then, so you get the same kind of piece by using the 48 pieces. So what I applied here is like, I try to apply this simplify algorithm, right? So where you started with the 82 vertices, and then, so you have dropped down into 48 vertices. So when you enlarge these two polygons, and you will see that there will be a tiny so there will be reduction of points, especially in these curved areas here and here. So then, to be honest, so the shape you the curve you achieved here will be different from the curve you achieved here. And so when you further simplify, so this kind of thing would happen. So if I want to show it to you, so we can do it like this way. And so now you can see how this looks like and how this looks like. Okay, so likewise, we can see that one. And also if you have a function like, if you want to know whether one particular polygon or one particular point or could be one particular line is within inside another geometry, so then you can use the within function, and then you can easily check whether a particular point is inside a polygon or not. Something like that you can check, because these kind of operations are needed when you want to check a certain cut template layout. And how can I forget about the buffers? Because buffers are also very important. And I think I forget one thing. Let me come back to the simplify again. So there is a part that I want to say here about, yes, one side you can think of reducing the number of points will damage the technical behavior of your curves. But the other side is, if you can make a compromisation on that one, think about the computational time point of view, how much it will be advantageous. Say, for example, if you are, when you are working with 82 pieces, and then when you try to say, let's assume you have 10 pieces of this, and then if you try to make a cut template layout, and the same thing if you try to do with this piece, like with 48 vertices, 10 pieces, so there will be a drastic drop in the computational time it takes. And the other aspect is when you try to integrate these concepts with the hardware components. Say, for example, ultimately these pieces will be feeding to a cut template layout, then you are going to cut it. So then when it's come to, when they are integrated with the hardware, so then it's all about moving the knives all over around these pieces to cut the and get the cut panel layout. So then if you have working with more number of vertices, so definitely your cut efficiency will be dropped. But if you can have a compromisation, so then you can think of like improving the cut efficiencies as well as sometimes blocking efficiencies. But you have to deal with this in a very careful manner, because always there's a trade-off between the computational time and the cutting efficiency versus the technical requirement of reaching the accuracy and reaching the correct fit. So this is about buffers. Yes, so sometimes we have to keep the buffers like this, especially when you are working with very small garments, and then sometimes corner points are really significant, and then so you want to maintain the real shape of those corner points. So in that case, sometimes people will think about buffers, as well as if you are using computerized cutters a lot. So once again, a buffer is a requirement. So in that sense, if you want to handle the buffers, so you can go to the boost geometry, these simple set of codes freely available, and then so you can do the programming with those things. When you have the programming ability, or if you are a researcher, you can experiment a lot of customized buffers around the pieces. So that kind of work you can do, and then experiment a lot of things, and then come up with new findings relating to this particular area. And also I discussed about the Norfolk polygons, and similar kind of work happens even when the boost controls the overlaps. It will find out quickly whether two geometries are overlapped or not. So if it is overlapped like these kind of two polygons, it says yes. If it is these two polygons, it says no. So that's what I feed it here. And then by applying a very simple function like this, so you can check whether two geometries are overlapped or not. Yes, so that was about managing the computational geometry part, and then that will be useful when you try to move the pieces around your layout. So when it comes to the development of actual layout, so we have two approaches. One approach is like you can survive with the constructive algorithm. Basically what happens is, that's what I actually explained there. So you can place one by one the pieces. Every time when you place a new piece, you get the union of the other pieces and then think about where to place. So then that way your solution construction will happen, and then entire cutting layout or the entire packing, the layout will be developed. the other option is, this is not within my scope for today. The other option is like you can preload all the pieces to the layout, and then it is allowed to have the overlaps. And then you can search over the layout until you will reach us to a position where no overlaps will be there. So that way also you can optimize the layout. But so this second approach is not that much common, but the first one is really common, and basically the solution quality, because so here one solution, here another solution for the same set of pieces, but you can see two different solutions actually. So basically the solution quality is based on the piece placement strategy, the way that you place the pieces and the piece rotations, as well as the sequence of pieces. Say for example, in this case, I put this particular piece first. In this case, I put this particular piece first. So two different pieces, which means like even though you work with same 30 pieces, so the piece sequence and the piece orientation strategies as well as piece placement strategies will change the layout. So in the first method, if you want, that will be really easy if you can follow up this kind of method. And then, so as placement strategies, you can think of like bottom left, which means, so you always try to pack bottom left. So something like that. And then we have another strategy called bottom left with hole filling. And there are many strategies. If you want to know about these strategies that you can experiment, so I recommend you to go to have a look on this paper. So by Benel and Oliveira. So the two main authors in this area. So then you will find a lot of strategies applicable for placing the pieces, and also piece orientations are like could be finite rotation, which means only these three angles are allowed within our rotation, or could be free rotation as well. And this is one of my works as well, my contributions in my postgraduate studies. So then according to these piece orientation strategies, so then you will have different layout. And also, so the piece sequences, you can do it randomly, or you can have some heuristic approaches. So you can generate different initial solutions and then lead into a meta heuristic approach like genetic algorithm. And then, or else finally, if you are a fan of mixed integer programming or maybe exact methods, you can think of developing a layout following exact method, but it will be really, really time consuming. So that's a method. And also you will be able to work with very less number of pieces. So I here just few ways of constructing the cut layouts. And if you have time, so maybe you can have a look on these research papers and then get familiar with that one. So that's about the developing a layout. But the problem here is like we cannot accept any layout as it is, even though they are not overlap, even though all polygons are placed properly inside the rectangular place. But how about the optimization? So that's one area that we need to work with. So I am presenting here one optimization approach, and there will be different optimization approach. If you really want to know about that one, go back to the same tutorial paper. So there they discuss a lot of optimization approaches as well. So I am presenting something that I work with. We give work based on Gauss-Lang and Benel from 1998. So basically, so this is a kind of nice heuristic. So I think you are familiar with, when you go to watch the movies or movie theaters, so it's a usual thing that you go and have a popcorn. So then what happens is like you get the popcorn filled one, but when you shake it a little bit, so what will happen is those popcorns will go a little bit down, right? So then you feel like there are more space to insert egg, right? The same thing, you can do it with the regular shape packing as well. So this is what I did for my postgraduates as well. This is one work actually. So you can place the pieces like this and have a nice layout, and then further place the other side. So in here I am using the bottom left approach, and then here this is bottom right approach. So it's like placing the pieces here and there from left to right, right to left, left to right, left to left. And meanwhile, you can see that some improvement will happen. And also, if you want to further see some improvement, if you want to see some further improvement, you can think of like applying this heuristic with iterated local search approach by implementing some kicks. Don't worry if you don't know these things. If you are a person from operational research, you will think of like this, but try to understand the strategies here. So then it applies this kind of simple heuristic, but reaches very good solutions. So yes, by using this knowledge, yes, we can think of like one stock sheet and you can place the pieces and then have a nice cut template layout. And sometimes you may think of like having different size of stock sheets. So then in that case, yes, we have solvers to solve that kind of things as well. So if you have a personal research person, once again, this will be like irregular shape being single size being packing problem. And this is like irregular shape, multiple being size being packing problem. And also sometimes after cutting, so you can see that some residuals are there in the stock sheet. So this could be a long fabric piece remaining after that having the cut template. So in that case, so you can think of like reusing these residuals as well. So because you could use this one in the next order sometimes, or maybe next cut order. So in that case, and when you have multiple cut orders happening in multiple scenarios or multiple periods, so can we think of optimizing that way as well, other than optimizing just one single stock sheet? So that kind of things are also possible and happening in the research area. And if we can get some success on those areas, so indeed we can implement them with different solvers and then think of improving the fabric waste gauges. So what could be the future? So the future will be after having this talk and then sharing the up-to-date research areas. Yes, still this cut template layout area is an ongoing area and it's still improving. There are more things to do in terms of handling computational geometry, in terms of optimizing the cut template layout. It's still the people in this area is struggling to find out optimized layout in a quick time. And a lot of parallel algorithms are going on. And also, the other thing is I want to emphasize when it comes to 3D shape or the virtual garment arena. So if you are a fan of this Seagull library, so yes, Boost will be highly cater on the 2D shape patterns. But if you are a fan of this Seagull one, so then you can work with even 3D as well. So it's not about polygons only. It's about dealing with the shapes and then dealing with measures, dealing with arrays of points applied in the 3D arena. And then you can think of there are different libraries available by applying simple coding. So you can think of like matching some curves to curves. So if you went to Dr. Jamali's one, so then she was stitching and basically she was trying to the virtual environment, she was trying to connect two pattern pieces together in 3D environment. So then what's going on behind that in the computational science point of view? So then if you have a look on this area, so then I am pretty much sure you will get some understanding about how the things are going on. So with that note, I would like to take the control to Christine. Thank you.
Yeah, thank you very much, Ranga. That was very interesting, very insightful. If you've got any questions, you can put them in the chat and I'm sure Ranga can respond to them in the chat. I'm conscious of time and we've officially run over as expected because there's just so much interesting stuff to cover in this workshop today. Yeah, thank you so much, Ranga. And that brings us to the final part of our workshop, which is about limitations of applying digital technologies. I'm obviously conscious that we've run over time, so I will try to keep it brief, but I'd really like to get some of your input in this last part as well. So hopefully you can stay with us for a bit longer. We'll try to wrap up. Limitations of applying digital technologies in apparel product development. So we've seen different technologies. We've looked at body scanning, automated pattern development, 3D CAD for virtual fitting and prototyping, and also marker making and cutting technologies. And I want to look at some of the limitations. But before we do that, I want to actually have a look at the promise. Before that they're making all of these promises, and for example here we've got Browseware saying that they're enabling apparel companies to digitally transform their business. They're promising true to life garment prototyping, accurate fabric draping. So then we've got Lecture here promising like 30% increase in pattern development speed, speedy approval, efficient pattern grading. So a lot related to speed. And I guess that links back to some of the benefits that you've identified when you think back to the introduction about 2 hours ago, when you said what the key benefit is for you in using technology. You highlighted speed there as well, and efficiencies. Which obviously Lecture is picking up here on. And then also we've got Optitex, and they promise here end-to-end digital solutions for fashion and apparel businesses, and a 60% faster sort of workflow compared to traditional supply chains. So yeah, that's quite interesting. And obviously speed and efficiency, it seems to be the case, because that's what you have all identified as a benefit. However, I have a question mark against these sort of claims of true to life garment prototyping and fitting and fabric draping. But I'll be talking about some of my own sort of experience of my research, where I came across some of the limitations in 3D CAD. But first of all, I'd like to ask you, and that's going back to the poll again, what are the biggest barriers to the adoption of digital technologies for apparel product development in apparel businesses? So I can share the link again in the chat if you're no longer logged on to the session. Or you can respond in the chat as well. So A, resistance to change, B, shortcomings of technology, C, system compatibility issues, D, skills shortage, and E, difficulty to integrate into current processes or supply chains. Interesting, we've got some responses here in the chat saying all of them. Yeah, so obviously there are still quite a lot of barriers there, because when we think about these promises that we've just looked at by the CAD companies, you'd be thinking like, why don't fashion companies actually employ all of these technologies? Because at the moment we don't really know what the adoption is of digital technologies within the global fashion industry. If you're looking at it from a global perspective, obviously here in Sri Lanka it's quite a high level of adoption of digital technologies, but I would argue that sort of an end-to-end solution of digital technologies and digital transformation is probably not commonplace in the apparel industry at the moment. And obviously looking at all of these promises and the efficiency gains, you would think like, why is that not the case? But obviously here we've identified there are some barriers, and a lot of you saying that all of these would be barriers for businesses. And let's see what the poll result is here as well. Okay, yeah, so so probably the least difficulty is the difficulty to integrate into current processes and supply chains, which is good. And skills shortage is interestingly the highest level here. And I think that's something that really needs to be addressed. Obviously from our point of view, from the education and higher education sector. But then also in terms of like, you know, coming up with new roles that will exist in the future in the fashion industry. Okay, interesting. So as I said, I'll try to be pretty quick and go through some of my research and the limitations that I've identified. So this is a study that I conducted a few years ago, and there's a link here to the publication if you're interested. So I won't go into too much detail, but basically what we looked at was we wanted to see whether we could use an existing clothing specific 3D CAD software, and in this case it was Optitex, to predict pressures applied by compression garments. So the idea was to use 3D CAD for new product development, because new product development requires prediction, whereas, you know, if you trying to just replicate something that already exists is basically just to create a copy of reality, but that's not what we wanted to do. We wanted to actually predict something before we actually making a prototype. And that's what we looked at. So we conducted in vivo wearer trials with participants with these compression garments, sports compression garments, and took body scans of the participants, measured the pressure that the garments apply to the bodies, and then we digitized the patterns and imported the body scan avatars into Optitex, and then created the simulations and used the pressure map that Jo Mali mentioned as well in her presentation to then compare the pressure values. And well, the short answer is it cannot be used to predict pressure, but that's not what I came to talk about today. What I want to focus on today is a bit like the different limitations that I came across when I actually tried to create a simulation of compression garments. And it starts with the import of 3D body scans into 3D CAD. So here we can see a 3D body scan that I've imported into Optitex, and as you can see here, there's sort of a bump on the body contour on the shoulder here where something was picked up by the scanner sensors. Then there's this webbing in the underarms, which is quite common with 3D body scans, either in the crotch area or in the underarm area, because the sensors can't really pick up the area there due to the light and the shadows. So again, here we've got the webbing, and here I've just included image C here to show you what it would look like if you actually virtually fitted a garment directly onto a 3D body scan. Obviously here, because of the webbing in the underarm area, there are gaps in the fabric. So what we had to do is actually retopologize the avatar to make it workable. And that obviously here we can come back to the skills gap that has been identified by you as a barrier. Again, I had to ask a computer specialist here to actually retopologize this in a 3D CAD software, MERcon, because that was outside of my skill set. And you would not expect a designer, product developer within a fashion company to have these skills necessarily to retopologize a 3D avatar. So here, obviously, this is like in process of retopologizing. So they removed that bump on the shoulder, they removed the webbing in the underarm, and then in the end, we had a usable body scan avatar. But obviously, that took a lot of time and specialist knowledge, and that's obviously a big limitation. Then the next limitation here we can see is virtually fitting of high stretch fabric. So this is obviously related to the fact that I've tried to fit compression sportswear, and compression sportswear is smaller than the wearer's body because it has negative ease in terms of pattern. So the patterns are smaller than the body in order to apply pressure to the body. And that's why here we came across some problems in terms of the stitching. So Jo Mali showed you the process of how to stitch the different pattern pieces together. And I mean, that's a whole different story as well, which it takes a long time when it's a complex garment that has lots of different pattern panels, like, as this one has. That's a time-consuming process, but once it's set up, it's fine. However, then when we try to sort of place the garments around the body in order to then fit it, you can see here that some of the stitches collided with the body because the pattern panels are basically smaller than the body. And then this in the end caused some issues as well, like some fabric gaps in the simulation. So it often resulted in like a failed simulation. So you had to process, which is obviously not ideal, not what you want in a product development process in a fast-paced apparel business. Okay, and then there are big limitations in the simulation of garments construction properties. So most of 3D CAD software will have some sort of parameters that you can change related to the stitches or seams used within the garments. Optitex has a few parameters, however, they are not directly linked to the actual physical properties of a stitch or seam. And here in this simulation, you can see that these red lines, those are actually the seams in the garment, and they're showing here extremely high pressures at the seams. So they were actually so high, they went above the capability of the pressures that a garment could apply to a body. So they were very unrealistic. So that just showed that the software was unable to really simulate the sort of flexible seams, and even like changing the properties of the seams did not really change any of these sort of high pressure levels. There was also a elastic at the waist, and again, it's very difficult to simulate sort of garment components like that at the moment, or realistically in terms of the technical properties and how it will affect the pressure application or the fit of the garment on the body. Then, of course, the key limitation is as well that we're simulating fabrics. I mean, simulating fabrics is very difficult anyway because of the anisotropic characteristics of fabrics, and that's why the sort of simulation of clothing and virtual fit lags behind other industries. Using hard materials, solid materials. But then it also needs to be simulated in combination with the body. So there's like geometric contacts between the fabric and the body, and that's really difficult to simulate. And as we found in our study, in terms of the pressure maps that we can see here of different participants, they did not directly linked to the actual in vivo pressures that we measured in these participants. And then there are also limitations when the fit is not 100% right. So as Simeon has mentioned, obviously there is a big issue with sizing. And we found the same with compression garments. So it was very difficult to find a well-fitting item for our participants, and in many cases the problem was the length of the garments. So the sleeves and the legs were too long. So rather than sort of in reality the fabric would have just bunched up at the ankles. It could not be represented here because it wasn't an ideal fit. It was sort of like wrapping around the lower leg, and there were lots of like trial and error iterations in order to get a proper simulation of these garments. And this is also something that was picked up in previous studies by Song and Ashdown in 2015. They also reported that there was a lower simulation accuracy for poorly fitting garments. So that's obviously a concern. If we can only fit garments that actually fit very well, then really, what value does it give to the process? Okay, but that's sort of like just some limitations that I picked up in my own research, and some of them are definitely specific to compression garments. So if you had garments with positive V's, it might be very different. And I'd just like to hear from your point of view and your experience, what the biggest limitations are. So what is the biggest limitation of digital technologies for your business and research? And this does not necessarily have to be related to 3D CAD. It can also be related to 2D CAD or anything else. We'd love to hear what, from your point of view, is the one, if you had to name one limitation, what's the biggest limitation of digital technologies? Again, we're using the poll for this one, so you can add this in the poll. You can just add one word, I think, if you open the, or you can add it in the chat as well, which is fine. Interesting. So we've got two people mentioning cost. So cost is definitely a factor. It's a high initial cost. Training, yeah. Again, we back at like the skills. So I've got a question here, whether we can get the pressure level on the advertiser value. Yeah, we can. So basically on the particular one, an Optitext, you can put your the cursor at any point on the body, and then you can get a pressure reading from that. Yeah, not just the color coding. Yes, could not simulate perfectly. So yes, so definitely some. Okay, let's have a look. What was that? Some training cost and initial cost are higher. Yeah, that's great. Okay, so I wanted to ask you guys for some ideas of the developments and or innovations that we need in order to get the most out of the technologies. Either new technologies that need to be developed or new ways of using technologies, just so we can all benefit, and particularly maybe focus on Sri Lankan manufacturing industry as well, of what do we need to do in order to get the most out of these technologies. And I know we're slightly running out of time, so I will put the link in the chat to this Jamboard, and you can add some post-it notes in there, and you can go away and post some more thoughts on there after the session as well, and we can then share the results with you later on. And we've got a comment here: some software companies developing their software to match physical garment look, since still it's not at least 70% matching. Yes, I agree. So from a technical point of view, there's definitely still a long way to go. We can create nice visualizations and rendering of garments, which can be used for marketing and sales. But I think in order to actually replace a physical prototype, I think there's still a long way to go. But yeah, so have a look at this Jamboard and add your comments on there, and then later on Jayamali can share the results with you, just to yeah, no, I can't, yeah, here it is. I've just, so this is what it looks like. So here you can use the force button here, this one here, to add a sticky note, and we can already see some people. Neat flesh dummy, yes, soft avatars, definitely, good idea. Incorporate artificial technology more, great, yeah. So I don't want to take up too much more of your time, but please do take maybe 5 minutes after the session and add your ideas to this Jamboard so that we can then share it with everyone later on. Okay, so I'll just go back to my presentation now. So yes, so have a think about the future developments needed, add them to the Jamboard, and then we can send you the summary later on. And lastly, I just wanted to say thank you very much for staying with us, even though we went over quite a long time. And thank you so much for everyone who's participated. We really value your input. And Jamali has asked me to ask everyone to put on their cameras, if possible, those who are willing to, so that with everyone on there who's willing to put on their camera. So yeah, if we can get some more people, then we can take a screenshot, and that would be brilliant. Are you taking a screenshot, Jayamali?
Yes, I will do.
Yeah. Yeah, good to see your faces as well. And thank you so much for staying with us.
Thank you for connecting. Sorry to exceed the 5 o'clock.
Yeah.
Yes, we had lots of person because we have 4 speakers and with very good contents. Thank you, Christine. Thank you, Dr. Simeon. Thank you for connecting today.
Thank you, Christine, and thank you, Simeon.
Yeah, thank you, everyone. Okay, see you all soon. And we can share the results with you afterwards if you add your comments to the Jamboard. Bye.
Bye.
Mm.